Good afternoon to everyone. I welcome all of you to the 78th lecture in the lecture series in nonlinear dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. It is my pleasure to introduce today's speaker, Prof.Andrew Pickering from Rey Juan Carlos University, Spain. Professor Pickering obtained his PhD from University of Leeds, England, in the year 1992. He started his academic career as a lecturer at Department of Mathematics, Heriot-Watt University, Edinburgh, and later worked at few other universities in UK. He then moved on to Spain in the year 1999. Initially, he was in the University of Salamanca, Spain, and then settled as a professor in the year 2004 at University of Rey Juan Carlos, Madrid. For the past 20 years, he is serving at various capacities in this university. Professor Pickering is working on integrable systems and delivered a large number of talks and visited several departments and collaborated with so many people. He has obtained a large number of grants from various scientific agencies to carry out his research. He has published several notable works in the area of nonlinear dynamics and integrable systems in particular. I met Professor Andrew in the year 2000 when I was carrying out my postdoctoral work at Department of Physics, University of Sydney, Australia, where he was a visitor to mathematics department. I also met his wife, Professor Pilar Cora, in Sydney, who is also working in integrable systems. Since all of us working in integrable systems, we quickly became friends. Later, he invited me to visit his department in Spain. We have jointly written a couple of papers in integrable systems. When I inquired the possibility of delivering a lecture in this forum, he immediately accepted. Thank you, Andrew, for accepting our invitation. With this short introduction, now I invite Professor Pickering to deliver his lecture. Over to you, Professor.
Okay, so I'd like to thank Senthil for his kind invitation to give a talk. Very nice to hear from him. And so, as he said, we met some time ago in Sydney, and he's visited Spain a few times, and we've got some papers together. So it's very nice to for him to invite us to give a talk here. So what I'm going to talk about today is something that's really, well, in part, it's what really we've been working on over the last few years, over some considerable number of years. But then on the other hand, it's something very particular because I wanted to point out a couple of things that are maybe less attention has been devoted to, and so there's a couple of ideas where, in fact, there's quite a lot of examples that are out there that could be looked at, or for which these ideas could be extended. So what I wanted to talk about was the idea of auto-Bäcklund transformations for Painlevé equations and a couple of extensions. So these are these two things that we've done a couple of examples, or maybe 3 or 4 examples, but we haven't really done much more. So first of all, the idea of extending this kind of auto-Bäcklund transformation to partial differential equations, and then their use in deriving semidiscrete equations. So anyway, so I'll skip this and just go. So the outline of the talk is as you can see here. So I wanted to talk about, first of all, a bit about the background, some of the main ideas, and then the kind and sections. Section 2 is really the sort of thing that we've been working on, and I mean, obviously we're not the only people who've been working. I should have said, sorry, at the beginning. So this is what I'm going to talk about today is joint work with Juan Manuel Conde, who was a student of ours, with Pilar Gordoa, with Zolong Zhu from Shanghai, and also with Jonathan Wattis from Nottingham. I should have said that. He's on the first slide, but I sort of got skipped. Anyway, so as I was saying, first of all, I wanted to go through a bit of the background and some of the main ideas. So this is really what we've been doing. And in particular, in section 2, talk about deriving ODEs and auto-Bäcklund transformations. So this is really beginning with integral systems and going down to ODEs and using the structure to derive auto-Bäcklund transformations. So all of this I'll explain in a few minutes. And then the first extension is towards auto-BTs so auto-Bäcklund transformations for PDEs. And then, so some time ago, it was observed that, so in section 4, I'll just go through known things, that auto-Bäcklund transformations for Painlevé equations can be used to derive discrete equations. And so we also have an extension there where we can, in fact, obtain semidiscrete equations. So all of these ideas I'll go through now. And so all the background stuff, I hope to make it clear. So today, I don't really want to talk about hierarchies or have very complicated things. I just wanted to present the main ideas. And really, I mean, if you look at what I'll be presenting, really, you'll see that it's the same calculation, really, all the time. So anyway, let's see. So, and then at the end, just some conclusions and some papers for a reference. So the background to all of this was so Painlevé equations. So I don't know what people have been looking at as far as that goes. So Painlevé at the turn of the last century, a bit before, became interested in the idea of using differential equations to define functions. So this was really quite a pure mathematical thing at this point. So this was based on the observation that many new functions satisfy differential equations. They decided to go the other way and to use differential equations to define functions. So this saw them introducing this Painlevé property, because if you want something to define a function, then, well, first of all, you want that function to be single valued. So what they wanted was to have differential equations whose solutions were single valued. And this is a bit over restrictive. And so because it's enough to look at equations where you avoid multivaluedness at what they call movable branch points. So this is really an extension of what happens for linear equations. So linear equations can only have singularities at fixed points. And so what they were doing here was saying, well, let's take our nonlinear equation and we're only going to accept branching at fixed points. So anyway, this is the Painlevé property, and they classified equations with this property, and this led to the 6 Painlevé equations. So these are 6 differential equations of second order that define new functions. So later, people started to look at higher order equations. So there's work by Chassis, Bureau, Cosgrove, and Cosgrove much more recent, of course. And anyway, so this work carried on. I mean, but then suddenly there was really renewed interest in this because of the discovered connection with completely integral partial differential equations. So this started with a paper of Ablowitz and Seeger in 1977, where they realized that they could basically take ideas from integral PDEs and solving equations via the integral equations, take those ideas across to Painlevé equations. So they looked at moving from modified KdV, so integral PDE, to the second Painlevé equation. And so really, and then we have Herold. Started, I mean, so Herold, she was the first person to actually consider hierarchies of Painlevé equations. So she had a P2 hierarchy. So whereas Herold and Seeger, they looked at the second Painlevé equation, what Herold did was look at the connection between hierarchies of partial differential equations and going to hierarchies of ordinary differential equations. So she had a hierarchy of differential equations of each even order, for which she then found auto-Bäcklund transformations. So these words I'll explain. So auto-Bäcklund transformation for ODEs I'll explain in a few minutes. And then Kudryashov was so, because this again lay dormant about this idea of hierarchies, not Painlevé equations, but the looking at higher order equations lay dormant really until Nikolai Kudryashov published a paper in 1997 when he refound the P2 hierarchy of Herold, the second Painlevé hierarchy of Herold, and also a hierarchy based on the first Painlevé equation. Anyway, so our aim in what we do in our research and other people, so what we want to do is to use properties of integrable partial differential equations and lattices. So we look at things like non-isospectral equations, Hamiltonian structures, mirror maps for, as I say, for integral systems, and use these properties to obtain Painlevé hierarchies and their properties. So in particular, today I'll be talking about using these properties to find auto-Bäcklund transformations, or auto-BTs. And then, as I said, we have these two extensions where what we want to do is to derive Painlevé style auto-BTs for PDEs, and then use these things to derive semidiscrete equations, even in the case of ODEs, in fact. So anyway, let's see. So to explain these things a bit more. So auto-Bäcklund transformations for PDEs for partial differential equations. So this is something central to integral systems, been known for a long, long time. So let's take this example. So what we have here is what's called the potential modified KdV equation. So this is a completely integral partial differential equation. And the two equations below are an auto-Bäcklund transformation. So these are two equations in Z and W, such that if we eliminate one of those variables, we find this potential modified KdV in the other variable. So this allows us to map between solutions, between one solution of potential modified KdV to a second solution of potential modified KdV. And in fact, this process can be iterated, and you will see that in this Bäcklund transformation, we have this arbitrary parameter k here. So this k, which appears in both equations, this k that allows us to actually generate multi-soliton solutions. So in this way, we can get multi-soliton solutions for potential modified KdV, and so also, in fact, for modified KdV itself. Anyway, as I said, so these are quite old ideas. So this is can be found. So good references or good or so there's the book by Rogers and Chadwick, and also the book by Lamb, and then obviously there's a lot more books where these ideas can be found. Anyway, so this is an auto-Bäcklund transformation for a PDE. So we have two differential relations between two functions, such that elimination of one yields the PDE in the other, and we have an arbitrary parameter in the transformation, which, as I said, allows us to generate multi-soliton solutions. And in the case of ODE, so here, in fact, what we have are two copies of an ODE. So this here, the first of these here, is the second Painlevé equation. Okay, so this is an ordinary differential equation in a variable y. So we have the second derivative is 2y cubed plus independent variable multiplying y plus an arbitrary constant. Okay, and this equation has auto-Bäcklund transformations. So what we have, in fact, is a map from one copy of this equation in a second variable q and parameter kappa, okay, to this equation in y and lambda. So it's a map between two solutions of this second Painlevé equation, which where we also have a change in the parameter that appears in the equation. So here there's two such mappings. So on the first line to the right, we have one of these. So this is y is q plus lambda minus kappa over 2qx minus 2q squared minus x. And we have a change in this parameter. So this tells us that if q satisfies the second Painlevé equation with parameter kappa, then y, given by this formula, satisfies the same equation, but with parameter lambda equal to minus kappa plus 1. And then below we have a second transformation, which is just a change of sign. So, so if q satisfies P2, the second Painlevé equation, for parameter kappa, then minus q satisfies P2 for parameter minus kappa. In fact, that's just a simple symmetry of the equation. If we change q to minus q and kappa to minus kappa, we see that we get the same equation back. So anyway, so these are the two Bäcklund transformations, auto-Bäcklund transformations for P2. So as I say here below, so these both relate solutions y and q of P2 with different parameters lambda and kappa. These two transformations can be composed, and in this way we can iterate to obtain sequences of solutions. So beginning, for example, with a trivial solution like y equals 0 for lambda equals 0, so that's an easy solution of P2. What we can actually do is iterate to find a sequence of rational solutions of P2, which end up being solutions for integer values of this parameter lambda. And there's one such rational solution for each integer value of this parameter. And there are other sequences of solutions like that. So there's also solutions based on area functions. Anyway, so the composition of these transformations allows us to iterate solutions, and these transformations can also be used to derive discrete equations. So I'll do this this last point I'll do explicitly later. So we'll do that later. Anyway, so let's think about how to go from PDEs to these equations and to their properties. So as I said, in particular, today I wanted to talk about auto-Bäcklund transformations. So here, in fact, so instead of similarity, so Abdevitz and Seeger and originally, including Nikolai Kudryashov, when they were talking about going from PDEs to ODEs, they use similarity reductions, and then so that's one way to do it. There's several ways to do it. Another way is to use non-isospectral equations. So this is where in the lax pair, the spectral parameter, instead of being constant, satisfies an equation, differential equation. So anyway, so here, and the connection with Painlevé equations was, and in particular with the linear problems of Painlevé equations, was observed by Levy, Ragnarsson, Rodriguez in paper 1992. So I should cite them here. So here what we will start with is, so the first equation here, this is, up to here is usual KdV, and then these, so we include here some non-isospectral terms. And so all of this, so the usual Mura map to modify KdV. So here we have this Mura map. So this goes between solutions of the modified KdV equation and solution of the KdV equation. So this all goes through for this non-isospectral. So there's nothing in this part I'm going to say which is really new. So this is really how to derive some known results. So as we see, this first equation, this KdV equation, can be written in terms of an operator acting on something, and this operator is the Hamiltonian operator of the KdV hierarchy, and with this Mura map, it can be factorized. So, and it's this that allows us to obtain the modified KdV equation, or in fact here, a non-isospectral modified KdV equation. So this is the factorization. So this operator here, d cubed plus 4wd plus 2wx, if we substitute W is yx minus y squared can be written in this form as the product of three operators. The first of these is the Frechet derivative of the Muir map. Then we have what is the Hamiltonian operator for the modified hierarchy, and then we have the adjoint of the Frechet derivative. And what's important really here is that this operator can be written as a product of things, and it's this that allows us to go to this equation here. So this is a non-isospectral modified KdV equation. And then here, what we can do is we can take the stationary flow. So we assume there's no t dependence. So our reduction to an ODE is very simple here. So we just get rid of the t dependence. And so we're left with this equation. So this equals 0. And obviously, since here what we have outside is just operator ddx, then this is easily integrated, and we get after some. So if we integrate, we include a constant of integration. So this constant of integration I've taken to be g0 plus lambda, where g0 is the constant now that appears in our equation, and we end up with this, which is just our P2. This is just the second Painlevé equation. So this was the observation of Levy, Ragnisko, Rodriguez, really, that Painlevé equations and their linear problems, so I haven't talked about linear problems, but these Painlevé equations can be obtained as stationary reductions of non-isospectral PDEs and also lattices. So that's what they did. And so this is a derivation of this second Painlevé equation. And in this equation, just by rescaling, we can set any non-zero. If G0 is non-zero, we can always assume that it's minus a half. Anyway, so this is deriving P2. So as I said, in fact, today we'll be seeing the same calculation several times. So what's important here is in fact this formula, so that we can write P2 in this form. This is one way of writing this second Painlevé equation here, and it's this that allows us to use to derive Bäcklund transformations. So this is probably I think this is probably the easiest way. So what I'm going to explain now is probably the easiest way to derive the Bäcklund transformation for B2. There are other ways, but then they involve a lot of algebra and anyway, so, and the point is, so if we go back to this Bäcklund transformation that we had here, so this is what I want to derive now. So this Bäcklund transformation, it turns out that with this Muir map, so here I had the Muir map, this quantity yx minus y squared. So it turns out that in this Bäcklund transformation, which is between one solution y and another solution q of P2, that in fact this Muir map is invariant. So in fact that the Muir map in y is equal to the Muir map in q. So there's this invariance. So it turns out, as I say here, that Muir in y is Muir in q. Anyway, so when a long time ago, so when I was young, we looked at deriving, so what was then topic of interest was using Painlevé analysis, so-called Painlevé analysis and Painlevé truncation to derive Bäcklund transformations for PDEs, and then we moved on to looking at to see what could be done with that for ODEs, and in fact there what we did was we made some kind of expansion where, because of the form of the expansion, it turned out that we had this invariance here, and that was assuming a certain form of expansion, which was equivalent to assuming that a certain Riccati equation was satisfied. We had this invariance. So, and then what I decided was that, in fact, to use this idea in reverse. So imposing this invariance, in fact, leads to a Riccati equation, which we can then use to derive the auto-Bäcklund transformation. And the advantage of this is that it's easily extended to discrete equations. So, because the problem really with expansion, with trying to take Painlevé truncation and Painlevé expansions over to discrete equations, is that it's not very clear what to do. Whereas if we're just talking about mirror maps and invariances and satisfying Riccati type equations, well, all of that can be taken over to discrete equations. So here the idea was to look for a mapping. So we're going to look for a mapping here like this, between a solution Q and a solution big Y here of P2, where we are going to insist in advance that we have this invariance. So it satisfies that this equation here is satisfied. Yx minus y squared is qx minus q squared. So we take two copies of the second Painlevé equation. So here, written in the form that we had earlier. So this, each of these are equivalent to the usual form here at the bottom here. Okay, so this is P2, but it can be written in this way. So we take our two copies of P2 in a solution Y with parameter lambda, solution Q with parameter kappa, and we ask that the mirror map is invariant. So if I take this expression for big Y and substitute in this equation here, okay, then what I end up with is precisely this condition. Okay, so the invariance of the mirror map is that this quantity here in this mapping satisfies this equation. And so in order to find our Bäcklund transformation, what we need really now is to find y, this little y, and the relationship between the parameters lambda and kappa in our two copies of P2. Okay, so what we do is we take this expression here for big Y, we substitute in P2, and then we just subtract the equation in Q below. And this determines Y, so this determines little y. But we're not finished, because this little y, as we know, has to satisfy this equation. Okay. And here we are using this, so we are using that we're assuming that mirror in Y is mirror in Q, because when I make this substitution, Y is Y plus Q, in here, directly this M of Y, I write it as M of Q, and it's this that allows us to subtract in order to find an expression for little y. Okay, so assuming that we have mirror invariance, we can find this part y of the mapping. But assuming this mirror invariance means assuming that this function that we've just found satisfies this Riccati equation in little y. So we have to take that into account, and so, but simply substituting into the mirror equation and using the fact that Q is assumed to satisfy its own copy of P2 gives us two possibilities for the relationship between lambda and kappa. So we can obtain either the identity transformation, or we can obtain this relation. Okay, and then this is exactly the relation that we have in our mirror, in our auto-Bäcklund transformation. So in this way, we end up with our auto-Bäcklund transformation. And as I said, we can always set this G0 to be minus half. And so this is just this well-known transformation. So in all of this, in deriving P2 and this Bäcklund transformation, what we've used are non-isospectral equations, Hamiltonian structures, and mirror maps. Okay. Anyway, so So I had further examples, but then, so I'll just mention, I'm not going to go through all these further examples because, in fact, otherwise I'm not going to talk about these extensions. So so what we've just done can also be done in the matrix case. Okay, so if we start with matrix KDV and matrix modified KDV, we have the same sort of structure. So we have a Hamiltonian operator for matrix KDV. We have a mirror map, the same mirror map. Okay, this is the same mirror map. And we have a factorization of the Hamiltonian operator. So everything I've just done before for this non-isospectral KDV and modified KDV goes through for the matrix case. With one slight complication in the case of matrices, I'm not going to talk about now, but basically, so we give an explanation in our paper. So this was a paper with Solong Zhu. This is myself, Pilar Godot, and Solong Zhu in Journal Differential Equations in 2016, where we derive this equation. Okay, so this is a matrix P2 equation. So precisely because it's matrix, we see here we have this these quantities. So there's no commutation here between what is our dependent variable u and this arbitrary matrix constant e. But this can be written in the same sort of way as before. Okay, so now we have this, where really the only difference is that instead of having, so whereas previously I had this operator d plus 2y, okay, which, so I take a derivative and then I multiply whatever I have to the right by 2y. Well, here we don't have that. What we have here is d plus au, where this au is a sum of left and right multiplication operators. Okay, so it's exactly this expression here. And obviously in the commutative case, this goes back down to multiplying by 2u. So as I say, so in this non-commutative case, we have a matrix P2. So the case E equals 0 was in fact found by Balandin and Sokolov, and by Over and Sokolov. And then, so there's a further paper where in 2010 where this was matrix P2 was also discussed, where in fact in a non-commutative setting, but where they obtained an equation like this one, but with a scalar e, which means that this e was assumed to commute with our new dependent variable u. Okay, so as I said, so this equation was the one we found in our paper, and in fact in this paper we had for hierarchies. Okay, so we had a matrix P2 hierarchy. Anyway, and we could obtain Bäcklund transformations. Okay, so for P2, going back here, remember that we had two Bäcklund transformations. So we have, first of all, this one, where we see in the denominator here, we have in fact twice the mirror map minus x. And then we have one where we have a change of sign. So in the matrix case, we have something similar, where here we have the inverse of this k, where we've replaced in k, we put w equals the mirror. So this is really the same as having, or the reduction to the scalar case is trivial because we already have here mirror plus a multiple of x, and it's inverse. So in the scalar case, obviously this is just division, but here this is an inverse matrix. So we have this mapping where we have a shift in parameters. So the first one here, there's no change in the matrix. The second one is a change of sign. So this is like what we have in the scalar P2. Here we have a change sign of parameter. There's no change in the matrix. And then these are matrix equations. So in fact, if you look at equation 1, and you just take its transpose, what you get is the same equation in the transpose of U and the transpose of E. So that means there's another mapping, which is this one here, where we can, so if V satisfies, so I say at the bottom here, so if V satisfies P2 with parameter kappa and coefficient matrix F, then we obtain solutions via these mappings of equation 1, which is P2 in U with parameter lambda and coefficient matrix E. Okay, so this last one is just a transpose for the same parameter and with the change in the matrix. And as I said, these are general formulae. So we have a matrix P2 hierarchy. So if instead of this K here, so there's expression is not just obviously not just arbitrary expressions. There's some very specific expressions for what these Ks can be. But so this was the first one, which gives us matrix P2, and then the second one is this one here, and this one gives us a fourth order matrix P2, which is this matrix equation here. So here is we have much more explicitly presented the non-commutativity, because in the scalar case, for example, these three terms here would go together. Okay, but these formulas for the Bäcklund transformations that we have on the previous slide, so these formulas here, in fact, go through for the entire hierarchy. Anyway, so I'll skip that because of time and talk about an extension. So here, in doing what we've been doing here, what we've done is we've taken structures of partial differential equations and we've used like the Muir map, and we've used those in ordinary differential equations having a certain structure. So here, having this kind of structure. And then we've said, okay, we can use that to obtain a Bäcklund. And now what we can do now is in fact think, well, what happens if we have a PD with this structure? Because there's no reason why we shouldn't. And in fact, we can do that. So this was the first, so this is one extension that we worked on. So this was, this is joint work with Pilar Godoy and Juan Manuel Conde in the thesis of the latter, and which was published in Journal of Mathematical Physics. So here we take something similar to KdV, but this is really an inverse KdV flow. So this is the AKNS equation. So this written down in 74, I think, by Average, Count, New, and Seeger. And is this equation. This is a partial differential equation where what we have here is the recursion operator for the KdV hierarchy. So the important thing here really is that we have out front this operator. So this is the B1 before, so because this recursion operator is B1 the inverse. And so in fact, our equation can be written as an operator acting on some quantity L, where this L is an integral of ut plus some other terms here. So this is a non-isospectral version of this AKNS equation. So the original one wouldn't have a g of t. But once we've got this one, then we can do the same as before, because if we go back to KdV, and our non-isospectral KdV, so we actually take G1 to be 0, ends up being B1 of something, and we have exactly the same here. So we take our PDE, and this ends up being B1 of something, ends up being B1 of this L for this L, where we have this integral of ut, but then that we can always sort out by taking some potential. And we have the same factorization because it's the same B1, it's the same Hamiltonian operator. So we can go over to an equation like before, where we have a derivative of d plus 2v of the same L, but now with u in L is replaced by the mirror map, and we can integrate and introducing a function of integration. So now a function of time, which we take in this form just because there's some cancellation when we write out the equation in the G. So this G here will actually cancel with something that falls out of here. Anyway, so we take our equation in this form and we can do the same as before. So the same calculation for deriving the P2 auto-Bäcklund transformation we can repeat here. So we can seek a mapping. So a mapping here between, so this would be a mapping between two solutions. One is W of our partial differential equation with this coefficient function now H tilde instead of H, mapping onto a solution V of the same equation for function H of T. Okay, so we take our second copy of our equation, we assume we have invariance of the mirror map, so again we have a Riccati equation, and we do the same. We substitute our mapping in our equation 2, and then we, assuming that M of V is the same as M of W, we can subtract, and we obtain this quantity phi here, and this phi has to satisfy this Riccati equation, because this is this equation that guarantees that we do have invariance under the mirror map. And so that then implies, so substituting phi in that equation and assuming that W does in fact satisfy the same PDE for a function H tilde, leads us to two choices. So whereas before we had parameters equal, here we have functions equal, or we had a shift in parameters, well here we have this shift in functions here. So in this way we obtain an auto-Bäcklund transformation for PDEs. So this is of a different form than usually considered for PDEs. So, as I said at the beginning, for PDEs we usually have a pair of differential relations and some arbitrary parameter. Here we don't have an arbitrary parameter in the Bäcklund, and it's an explicit mapping. We express V directly in terms of a solution W. So this is really analogous to what we have for the Painlevé equations. Okay. Anyway, so as I said, we have in this L, so go back to L, we have this integral here, we have this integral of ut. So let's write this mapping that we found. So this mapping we can find anyway, but we can now put this all in local form. So our equation can be written locally as this system. Okay, so what makes it local is this. Okay, so we introduce a new variable y such that its derivative is v squared. So in this way we obtain this pair of equations. So using this first relation, our equation becomes this. And so now we have three variables. We have v and y, and also the function h. So our mapping is then expressed in this way, and we have this relation between two functions h. So this is a mapping from two. So what we would have is a mapping to this equation, which is our system in v and y with additive function h, and we have a mapping from a solution of the same system in w and z, an additive function h tilde. So this is an auto-Bäcklund transformation for this system. So this is in this local form. And we have a second Bäcklund transformation where we just have a change of sign in v and h, which means we can iterate solutions. And so this we looked at in a paper again with Pilar and Juan Conde in 2012. There we actually looked at two sequences of solutions. We looked at solutions generated using this Bäcklund transformation, and also solutions generated using the standard kind of PD Bäcklund transformation that I talked about at the beginning. Anyway, so this is one possible extension of all of these ideas. So instead of So whereas we have Bäcklund transformations given as explicit mappings with shifts in constants for Painlevé equations, what we have here is these transformations given explicit mappings with shifts in function, and this is for partial differential equations. So it's interesting that applying PD ideas to ODEs and then lifting this back up to PDs again. So this is what we've done here. So again, there's matrix case, but I'll skip that because then I want to go on to the second extension here, which is this idea of going to discrete equations. So again, let's go back to P2. So this is our second Painlevé equation, and we have two Bäcklund transformations. So this is the first one, and here we have the second one. Okay. So what we can do is take compositions of these Bäcklund transformations. So the first, so I take these two compositions below. So the first of these compositions here, for example, is obtained by applying the first of the Bäcklund transformations written on the second line, and then the second of those. So if I apply the second of those, then here I would have minus y. Here I would have minus lambda, and then this relation would become lambda is kappa minus 1. So that will give me y is minus q. This will be minus lambda plus kappa, but then I have a minus coming when I do this, when I'm from here. So what I end up with is y is minus q plus lambda plus kappa over this denominator. But lambda plus kappa, now that lambda is kappa minus 1, gives me 2 kappa minus 1. So this first composition here consists of applying this transformation and then secondly this transformation. And the second composition below here is obtained by applying first this transformation and then this one. Okay. So we have these two Bäcklund transformations. So, and here we see that the first here takes a solution q for parameter kappa to a solution y for parameter kappa minus 1. And the second one takes a solution q for parameter kappa to a solution y hat for parameter lambda hat, which will be kappa plus 1. Okay. So manipulating these formulas, so for example, the second of these compositions tells me that 2 kappa plus 1 over y hat plus q is this quantity. And the first of them tells me that 2 kappa minus 1 over y plus q is this quantity. So adding those, the derivatives disappear on one side and I'm left with this quantity. So it's just a simple manipulation from these two compositions to get down to this equation, where instead of y, I write q in kappa minus 1, okay? Because that's my solution of P2 for kappa minus 1. And instead of y hat, I write q for kappa plus 1. So, for example, in this 2 kappa plus 1, where I would have in the denominator y hat plus q, that is now q in kappa plus 1 plus q in kappa. So this is now a discrete equation. So, because I can consider q to be a function of this variable kappa, and I have shifts in kappa. So this was derived by Fokas, Grammaticos Romani, and also by Gromak and Sirgelnich in a paper in 93, 94, these papers were published. So this is another idea, the standard idea being exploited by several authors already, of going from Bäcklund transformations for Painlevé equations to discrete equations. So this is matrix case here. So what I wanted to talk about here was to do this for to go to semi-discrete. So instead of getting here a purely discrete equation where what I have is a dependent variable that depends on a discrete variable kappa, I want to go to an equation where I also have derivatives with respect to other variables, a semi-discrete equation. So if I go back to this PD system that we had, I can look at composition of so I had Bäcklund transformations written for the local form, and I can look at compositions in the same way. So this would be the first composition, and this would be the second composition. And then what I do is I take the V and W parts and I do the same manipulation as before. So I get this equation. And the last equation on this slide here is when I take the Y and Z parts. Okay. So I go over to these two equations. So these are PD analogues of this discrete equation here. Okay. So if I want to go, sorry, if I want to go now to a semi-discrete equation, what I can do, for example, is just to assume, so I can always take my function g to be minus a half, in fact, so I said that at the beginning, this can always be done. So that's why here I have this term, instead of plus 2g0, plus 2gx, v, I have minus xv. But so if I now set this h tilde to be kappa, so this is now similar to before, the first of these equations, equation 6, becomes this one here, but I still have this time derivative of z on this side, and z is related to w in the same way as y is related to v. So I have that zx is w squared. So I have this equation, which involves shifts on kappa, but also with a zt coming in, where this relation is also satisfied. So I have a system, or which could be written as integral differential if we want, but I have this system of equations, which is semi-discrete, because what I have is shifts in one variable and derivatives with respect to another two variables. And this can be reduced to what we had before, simple reduction. So the same reduction that takes us down to P2 and the Bäcklund for P2 was also, we can do the same for this discrete equation, and we can go back down to what was called, sorry, I didn't give it its name, this thing here, which is called an alternative discrete P1, okay? Because it has a continuum limit to P1. So we can go back down to here, and it's easy to see, in fact, that this transformation, that this reduction would work, because it consists in taking our a single new, so it's a reduction, so we have a single new variable, new independent variable xi, which is x plus t, which means that ddx is the same as ddt. So this zx here is the same as this zt here, which means that we end up getting a w squared in this part here. So this becomes 2w squared. So that's exactly what we have here. This is this 2q squared. Yeah. Anyway, so that's the first. So that's one equation. And then also from this equation 7, where I have y and z, doing the same here, setting h tilde to be a constant kappa, we can derive this equation. Okay. And here we don't have a second order auxiliary equation because we only have z in this equation. Okay. So it decouples. We get this equation z, but so we have t derivatives and we have kappa as a discrete variable. And this equation can be mapped onto this one here. So a sequence of transformations, we can take it over to a new equation in some variable s, which is a function of kappa and a new time tau. Okay. And this is a lattice equation. And what's interesting is that, in fact, the second one here, going to this lattice equation, all goes through, even for the ODE case. So, in fact, whereas before what had been derived from P2 was this purely discrete equation, it turns out that you can also derive this lattice equation here. So this is a known lattice equation, in fact, this was known. So as I say, this also holds in the ODE case, and then we've done this for the matrix case as well. Okay. So should be finishing. So conclusions. So the three first points here is really what we do normally. So this is what we want to do, is to use structures of integral systems to derive Painlevé equations and their properties. In fact, this can be done for lots of different kinds of equations. So here I've talked about differential equations, but this can be done for discrete equations. So all of these ideas, even for differential delay equations, or with dependent variables, which are matrices. So here I've concentrated on auto-Bäcklund transformations. So the other aspects of Painlevé equations are interesting to obtain. And what I've wanted to give emphasis to today are these two extensions here at the bottom, where that we can get Painlevé style Bäcklund transformations also for PDEs, and we can use these Bäcklund transformations to derive, even in the ODE case, we can derive not just discrete equations, but also semi-discrete equations. Okay, so that's the end of my talk. So these are some papers where most of these are cited in the talk, and then there's one or two that aren't, but also contain relevant material. Anyway, so that's the end of that. So thank you everyone for listening, and anyway, so that's that. So.
Thank you, Andrew. So now the forum is open for questions, clarifications, doubts. Students, you can raise your questions either in the chat box or okay, let them think. Andrew, I have a couple of questions. This factorization is unique.
Sorry?
Factorization. You consider some factorized form. Whether this factorized form is unique.
Well, of the Hamiltonian operator, you mean?
Yes.
Yeah. Well, so it's unique up to, well, as far as I know. So you mean?
This you consider three.
As far as I know, it's unique
yes.
up to some change of sign, because modified KdV is invariant under u goes to minus u. So when we have this factorization here.
Yes.
Yeah, this is. So you can have because you have. So this is a map. This mapping goes from. So here I have an operator in W related to the product of three operators in Y, where we have this relation. So this is the Mura map. W is yx minus y squared, and y is a solution of modified KdV. Modified KdV is this one here, and this equation is invariant under change of sign of u. So this is unique up to this. So I could have here the same formula, but replacing y by minus y, in fact.
Okay.
So which would mean that instead of this m prime here would then be d plus 2y. And it's different, so the Mura change, but this is, I mean, yeah. But as far as I know, this is unique. Yeah.
Okay. I have one more question. Is there any attempt which has been done for other kind of equations rather than Painlevé equations?
If there's any?
The same study has been carried out for other class of equations. other than this Painlevé equations.
But which study for finding?
Riccati chain, Abel chain, like that. It's a chain of equations. We can start from first order to nth order. Riccati chain. From Riccati chain, you can generate a third order equation. From third order equation, you can go to fourth order equation.
Yeah, so these are, so I think, so the ones you mentioned are, I think are autonomous equations. So, whereas these Painlevé equations are non-autonomous, but in fact, you can, so I don't know of any applications to the equations you mentioned, but in fact, in a paper with, so in the paper I mentioned with Pilar and with Zolong Zhu, we did look at these transformations in the autonomous case. So this is after, so this was really the reason of having this G0 in here, okay? Because here we have P2 with a G0, which, as I said, if it's non-zero, can always be taken to be minus half. So this is, which is just a standard P2, but we left this G0 in as a constant. So because we wanted to be able to set it to 0 as well. And so in this paper, which was in Journal of Differential Equations in 2016, so that's Pilar Godoy, Zolong Zhu, and myself, we did actually have some things for in this autonomous limit. And in fact, and in the autonomous limit, in the stationary case, of course, what happens is that what is P2, so if we go to P2 here, but in this autonomous limit means without this term, without this xy term, well, this can be integrated in terms of elliptic functions. So in that case, what we ended up with was relations between elliptic functions. So these mappings transformed into relations between elliptic functions, but that's in that paper. But I mean, other applications to of what we've been doing of these ideas about no, I'm not aware of the application of the sort of thing I've talked about here to autonomous equations like the ones you mentioned. No.
Okay, thank you. So
Yeah.
are there more questions from the students? Students, do you need some clarifications? They are a bit hesitating. Okay, since I am not receiving any questions from the students.
Yeah, okay, don't worry.
Yeah, maybe they will like to, yeah, I don't know. Okay, since there are no more questions, I would like to conclude the session by thanking Professor Pickering for accepting our invitation and giving a very wonderful talk on Bäcklund, and the elementary talk on Bäcklund transformations. Thank you.
Okay, thank you very much. Thanks. Nice to see you.